So from the previous session, if you have k objects and you encode the information into a string about those k objects, then you just put commas between them and the angular brackets. So if you see that kind of thing as your input string, you know it's talking about an encoding, a representation of k of your objects, whatever they are, encoded in the form of a string. That's what the angular brackets means. Now, the actual encoding, there's different levels of efficiency. You can encode efficiently and inefficiently. That matters, I suppose. But it doesn't matter too much about how you encode, the different ways to encode, because whichever way you do choose the manner of encoding or the representation you choose for your string, the Turing machine can adapt to that encoding, because when you think about it, the program in the Turing machine, it needs to know what the encoding is. It needs to know what the representation is, so that it is able to extract the information about the objects that you're talking about. Okay. So your Turing machine can adapt to your method of encoding, to your representation of the objects that whose information you're feeding into the Turing machine as a string. Right. So and a Turing machine, it can always encode. It can translate one encoding into another one if necessary. So that's what I'm saying here. Okay, so how to now we're talking about a standard format, a standard way to describe an algorithm. In other words, a Turing machine algorithm. And that means, how do you write down? How do you describe the algorithm that the Turing machine goes through, in its various stages and so forth? What notation do you use, and how does it look? What's the formatting and so forth? Well, you'll typically your algorithm, your Turing machine algorithm, it'll just be indented blocks of text. English prose, in other words. Indent, what does that mean? If you're not a native English speaker, to indent means just to shift a block of text, a phrase or whatever, usually to the right. So in other words, to indent means to put spaces, usually on the left-hand side. Here's an example towards the end of this session. Can you see the spaces here? This block of text here, it's been shifted to the right, so these two lines here have been indented, right? moved to the right, and here are just blanks. So indenting is to put blanks on the left-hand side. It's usually the left-hand side. Okay. So here's an example of a description of an algorithm, a Turing algorithm. So you just English text indented. The whole description starts with a double quote mark. I can see it down here, the very bottom here. You have the end quote, the double quote mark here. Okay. So now I'm going back. So you're describing the Turing machine algorithm. So it's indented, segments of text, just English prose as usual, within quotes. You saw the quotes. See later for an example. We've just seen that. All right. Now, typically, you'll break the algorithm. I just shorten algorithm to ALG for obvious. It's pretty obvious. Into stages. And typically each stage will be given a number, stage 1, stage 2, and so on. And a stage corresponds to some obvious part, component to the processing that's going on, the computation. And usually one stage, will comprise many steps, Turing machine steps. That's pretty normal, right? Now, I've been saying in this standard way of describing an algorithm, Turing machine algorithm, is the first line describes the input. It describes the input string. Okay. Now, if it's just simply a string, if the input's just W, like a string, then you interpret that W just to be it is a string. Okay. Now, if the input is in encoded form, you'll use the angular brackets. So you'll use this in your first line, because your first line is talking about your input string. And so if you see these angular brackets, you know that the information going into your Turing machine, into the algorithm, is encoded. The angular brackets tell you that. Right? Now, whatever encoding you use, or representation you use, same thing effectively, then you're going to have to program your Turing machine to extract that information. So if you have incorrectly encoded, if you've made mistakes in the representation, so that the Turing machine with its programming cannot extract that information, so that it cannot decode, well, then that string gets rejected. Okay? So that's what I've been saying here. Now, let's do an actual example of a description of a Turing algorithm. What is an algorithm? And we'll see an example. Well, it won't be on this board, but next board we'll see an example of encoding or representation. They're synonymous, those two, effectively. So we'll see how to take the particular problem, the particular object we're talking about. In this case, this example, so 3.23, the object we're talking about is a graph. It's a graph, and a particular kind of graph. It's this is an example of a high-level description of an algorithm, Turing algorithm. So effectively we're describing the Turing machine that implements the algorithm, because they're synonymous, right? Algorithm means Turing algorithm. So it's an algorithm implemented by a Turing machine. I've said that many times, but it's critical. Okay, so what is the example? Well, we'll have a language, and we'll call it A, capital A for language. And a language, remember, is just a set of strings. So what are the strings in this language? Well, they're representations of graphs. And in fact, undirected graphs, that means there are no arrows on the edges between the nodes of the graph. Okay, go back to chapter 0, the preparatory chapter of this course, if you're forgetting about graphs. Okay. So your strings will represent undirected graphs, but they have another property. These graphs are connected. Can you remember what that means? That means it means that you have no. That means that every node in the graph can be reached from any other node in the graph. And reached means you just there's a path from one node, from any node to any other node in the graph. So you just find a path from one node to the other, to any other. And a path is just a sequence of edges, from A to B to C to D. Okay. Yeah. So connected. So every node can be reached from every other node via the edges of the graph. Okay. So here's the language. Now it's in the format, well it has to be because it's it's an infinite set, right? All possible undirected connected graphs, well, there's an infinite number of them, right? So we've got angular brackets here, so that means that our information about the graph, so this member here of the set, it's a graph, it's an undirected connected graph, right?